Hello, I'm Mike McCulloch. Today I'm going to try and convince you that mass is equal to proportional or even equal to area, which sounds rather odd, but I can promise you that that is what the data says. So the way to approach this, I think, is from the data. So here I show a table which has several columns on it. So the column on the left tells you the object I'm talking about. Then its observed mass is shown in the second column. Then its size is in the third column. And then I've calculated the area simply by from the size by squaring the side and multiplying by pi. And by area here, I mean the cross-sectional area. So it's not the area of the surface of the object, it's simply the cross-sectional area, pi r squared, where r is a radius. So we first have the electron, which is in the first row, and the mass is about 10 to the minus 31. So I've just shown the exponents here because this is fairly loose, but I'm going to prove it over a massive range of sizes, so perhaps you won't mind. So the electron mass is about 10 to the minus 31. It's actually 9.1 times 10 to the minus 31, but I'll just put the exponent there for simplicity. And its size, well, it's not quite clear what its size is, but it can be estimated to be about 10 to the minus 15, which means that its area is about 10 to the minus 30 in meters squared. So, okay, we have a reasonable agreement here. So the mass is 10 to the minus 31, and the area is about 10 to the minus 30. Now we look at the proton. Second row is a proton, and this is probably the worst agreement of the lot. So the mass is about 10 to the minus 27. The size is about 10 to the minus 15 again. And the area is 10 to the minus 30, so we're about 1,000 times out. But most of these are much better than that. Then I'm going to look at a flea egg. I just chose this as a kind of a small object within our realm of experience. The mass is about 10 to the minus 8 kilograms. The size is 10 to the minus 4. So the area is 10 to the minus 8, so it agrees with the mass. Then we have a table, kitchen table, which is about 20 kilograms and about 2 meters long, and so the area is about 4 meters squared, so again, within the right order of magnitude. Then we have a galaxy, so the Milky Way is about 10 to the 41 kilograms, that's just the bit we can see. The size is about 10 to the 20 meters. And the area is about 10 to the 40, so again we have within a factor of 10 agreement here. And then the entire cosmos, well, of course the mass is not particularly well known, but it's thought to be something like 10 to the 53. The size is about 10 to the 26, depending on which definition you use, and so the area is about 10 to the 52, which is close to the 10 to the 53, it's fairly close. So you can see here that over a massive range of scales, well, in mass of about 80, 10 to the 80, a range of 10 to the 80, and in terms of size, about 10 to the 41, a massive range of scale, that mass is roughly proportional to, and in many cases, just about equal to the area. Now this may come as a shock because whereas used to thinking of mass being determined by the volume, as it should be. I mean, you count the atoms, and the more atoms you have, the heavier it should be. But in these cases, it's not true. Now this is kind of interesting because you could say that mass is proportional to area, but this is showing that in many cases it's actually equal to the area. And I think the clue to that might be in the middle of the table. So this actual row labelled table. Because the reason for this is that we could well have invented our units to be convenient so that a meter is meant to represent something that we're familiar with on the scale of a table or a chair, and also a kilogram is supposed to be something that we're familiar with. So it's not a surprise that in this case the meters and kilograms are more or less the same, because we've designed these units to fit the things that we can see in our everyday life. And then when you extrapolate this with the obvious dependence from this table of mass on area, then you build up the apparent fact that mass actually does equal area. But why does it equal area? Why not volume? Well, quantized inertia predicts this, because it states that in every volume there must be enough gravitational acceleration so that the underwaves seen by objects within that volume do not exceed the size of that volume, of that cosmos. So you can write this like this. So gm of r squared is must be greater than or equal to 2c squared over theta, where theta is the cosmic diameter. And then if you rearrange this, so you have mass on the left hand side, then on the right hand side you have 2c squared over g theta all times r squared. And if you put in the values for c, for g, and for theta that we know, that we've observed, you get a number for this part of the equation that is very close to pi, which is very interesting. And so you can say that mass equals area. Mass is pi r squared, area. So quantized inertia predicts that mass equals area, and it seems that the observations back that up. And yeah, so I hope you are convinced that mass is area, and quantized inertia predicts it. So if you want more debates about this, I'll probably write something on my Patreon account, so please subscribe there. And you can now become a member of my YouTube channel, so please do that if you feel like it, if this is interesting to you. And many thanks for my followers on Patreon, and I look forward to seeing you next time. Goodbye.